Okay, so welcome to this week's Astrobiology Colloquium. So this week's speaker is Alfonso Davila. He's a scientist, research scientist at NASA's Ames Research Center in the San Francisco Bay Area. He did his PhD in Germany, in Munich, at the Ludwig Maximilian, whatever it's called, University, LMU, let's call it that. I get the pronunciation right. That was in 2005. Then he went to NASA Ames to do a postdoc, working with Chris McKay and others. And he loved it so much. He's been there ever since, basically. After the postdoc, he was a research scientist working through the SETI Institute for a while. And then in 2017, became a NASA civil servant. He's from Spain originally, but is thoroughly Americanized American citizen, NASA civil servant. Alfonso works on life beyond Earth, very much in the realm of astrobiology, and has published a lot about Mars and icy moons. And he's going to tell us about the latter today. So please take it away.
Thank you. Thank you, David. And I'm slowly losing my voice. I think that's because of all the good conversations we had today, but hopefully it'll last 45 more minutes. So I'm going to just count on the time here. Thank you for having me. It's been a great day here so far. It's good to talk to colleagues in academia. Now at NASA has remote work opportunities, teleworking, so I never see anybody when I go to work, and seeing all these many people at once and talking about all different subjects that you guys are working on has been great. So, but today I want to talk about one of the topics that it's been a passion of mine for the last 5 or 6 years after I did a small transition from Mars to ocean worlds, specifically this one in Enceladus. And hopefully by the end of the lecture today, you will understand why I think this is one of the coolest places for a vacation these days, Enceladus. And the talk is divided in 3 main parts. The first one is about Enceladus. I'm sure most of you have heard of it, so I'll just give you a few ideas of what this place is about and why we think it's a great place to go visit, search for evidence of life. The second part is probably the meat of the presentation, is what to look for when we search for evidence of life. Or at least that's what a whole lot of my own personal opinions, and also what not to look for and why. And then at the end, there's a few slides about a mission concept we put together a couple of years ago for the planetary decadal survey that just came out called Orbilander, and it's a mission concept to search for evidence of life on Enceladus, hopefully sometime in the next 20 or 30 years. So I'll give you some details about that. So Enceladus happens to be a tiny moon of Saturn. It's only about 500 kilometers in diameter. It's mostly composed of water, although the density tells us that there is some rock material in there. There's probably a rocky core, and then the rest is a water shell. The surface is completely frozen. Obviously, extreme conditions on the surface, nothing that is astrobiologically very significant. And it just has enough gravity to make our lives very complicated when we want to do missions there. It's big enough that it's difficult. It's difficult to stay in orbit. It's small enough that it's difficult to slow down and land on the surface. So it's a complicated engineering problem to design a mission that actually lands on Enceladus and searches for evidence of life. But you'll see in the end, we have a cool concept for how to do it. And for those astronomers in the room, if there are any fun fact, Enceladus is probably appears to be the source of the E-ring of Saturn, which has been known for many decades, but it wasn't clear what the source of the E-ring was. This diffuse ring around Saturn, and it turns out to be material coming out of Enceladus, and that's probably pretty much the focus of a lot of what I'm going to talk about today. There's a lot of banners coming out here, which is fine. Just closing them.
Lost the Zoom people. I don't know.
We'll see who wins the banner bundle. Okay, so a lot of what we know about Enceladus comes from the Cassini mission. That was really one of the most successful missions I think NASA has ever had, for many different reasons, not just because of the science Cassini did, but also for how the mission could actually turn around, literally in the middle of the mission. They could turn it around and target something that they weren't ready to target, which was the discovery of active plumes on Enceladus. Cassini was designed primarily to study the Saturn system, Saturn itself, Titan, and then to do a bit of a survey of the Saturn system. They weren't ready for what they found, which was a lot of material coming out of the south pole of Enceladus. And what you see there large is a picture of Enceladus south polar terrain, and you can see jets of material coming from the surface. And then the inset is a picture of looking down into the south pole of Enceladus, where there are these 4 giant fractures called tiger stripes, many miles long, a few miles across. And this is the source of this material coming out from the surface. And all these dots, those circles, all the circles you see there in that inset, these are jets that they could map with images from the mission, from the by the spacecraft, active jets, active locations where jets are being actively ejecting things into space. And so they actually managed to turn the mission around and target the plume and fly through the plume multiple times and analyze the chemical composition of those icy materials, which turns, I mean, if you think about it, it's quite amazing that they could do that. And in total, Cassini flew by the plume 22 times. They were orbiting Saturn. They weren't orbiting Enceladus. So every now and then, the orbits would be such that they could fly through the plume. They were going at very high speeds, anywhere between 10 and 20 kilometers per second. That's actually the way some of their instruments work. They relied on very high speeds to be able to detect some of the things that you could see that they detected. And so they flew through the plume 22 times at different elevations and at different orientations. And they got a pretty good picture of what the structure of the plume is and what the chemical composition of the plume is. And that motivates a lot of what I'm going to talk about astrobiology. Another thing they did flying over Saturn was to look at how the gravitational and orbital anomalies of the moon could tell us something about the structure and its internal structure. One of the things they learned is that this libation movement of the moon is better explained, which is the kind of motion that you see down there. That's our moon, that's Earth's moon. But that kind of libation motion that they see, that's what one of the main lines of evidence for them to conclude that there is a global ocean of liquid water under the ice shell of the moon. It's not a partial ocean under the South Pole. It's actually a global ocean. So you have this 3-layered structure with a rocky core, an ocean that is probably anywhere between 50 and 60 kilometers deep, and then the ice shell, which probably ranges in thickness from 2 kilometers, 5 kilometers, 5 to 10 kilometers in the South Pole to maybe 10, 20 kilometers, maybe even more elsewhere on the moon. And the South Pole is where you have this plume activity. Very interesting. So obviously the presence of a subsurface ocean in contact with the rocky core is astrobiologically very interesting, because now you can have a whole lot of things happening there that are astrobiologically relevant, like water-rock interactions, the dissolution of components from the rock that can be biologically interesting into the water column, and the fact that we can collect free samples by flying through the plume and analyze that composition obviously is very cool. So Cassini, partially probably due to the way they collected measurements, but this is probably reflects pretty much the structure of the plume. Cassini detected 3 different types of grains coming out into the plume. Disclosure, by the way, a lot of the Cassini results were based on E-ring analysis of the E-ring particles, not directly the plume. But we know the E-ring is just all plume material being left around as Saturn orbits, Enceladus orbits Saturn. So it's all plume material. They did a lot of their analysis on the E-ring material, but eventually they flew through the plume and they could confirm that what they saw in the E-ring is very similar to what they see in the plume. And essentially they found 3 different types of ice grains coming from the plume. Well, let me backtrack for a second. The plume consists of 2 main things: icy grains and gases, gas and ice particles. And the ice particles, they're divided into 3 main populations. They call them type 1, type 2, type 3. Can make 2 things too complicated for NASA. Type 1 are icy grains made of almost pure water, 99% pure water. Type 2 grains, which I'm going to talk a bit later about more, are organic bearing ice grains. And you can see a spectra here collected by one of the Cassini instruments, the CDA instrument, where you can see some of the spectral features that the instrument team, based on a whole lot of experimentation in the lab, concluded that those are organic fragments from organic molecules, along with spectral signals of water. And then type 3 grains, those are salt-bearing ice grains, and they contain primarily sodium salts, sodium carbonates, and potassium salts, some chlorine in there. So this starts to paint a very interesting picture of a subsurface ocean of liquid water. There is slightly salty, probably the salinity is similar to ocean water, maybe it's slightly less than ocean water, but which also contains organic compounds. Now, details of that geochemistry, when you can couple it with geochemical models, it allows you to infer a few properties about the ocean, like the ocean pH and its larger composition, and then analysis by the CDA instrument of the icy grains and another instrument called the INMS, which is a mass spectrometer to analyze gases. All that together paints a very interesting picture of habitability. What you see there in the upper right is a table with the gas composition of the plume measured by INMS. It's most of the gas is water, but it does contain a fair amount of CO2, methane, hydrogen, and nitrogen or CO molecules, maybe some ammonia in there. Now, the CO2 and the hydrogen is what got astrobiologists very excited, because that, as you will see in a second, that forms a redox couple that some organisms on Earth can use as an energy source. So now we're coupling an environment that could potentially host life with conditions that are needed for life to exist, like an energy source. So the detection of CO2 and hydrogen was a big result, a big deliverable from the mission. And based on the composition, the salty composition of the ice grains, the current understanding is that the ocean pH is probably somewhere in the alkaline side of things. It could be as high as 12, it could be as low as 8. Probably the best estimates are somewhere around 9 or 10. So an alkaline ocean. And another thing that Cassini detected were those silica nanograins, and you can see the spectral signature here of silica, which was interpreted to be nano silica grains generated at the bottom of the ocean. And that was one of the lines of evidence that the Cassini team used to argue that there is ongoing alkaline hydrothermal activity at the bottom of the ocean that is responsible not only for the formation of the silica nanograins that are eventually ejected in the plume, but it's also responsible for some of the chemistry that we see, the pH, the alkaline pH, and the salt composition of the ocean. Those are all consistent with an environment where you have alkaline hydrothermal vents. That's another thing that got astrobiologists interested, because alkaline hydrothermal vents are one of the places that people have postulated could be a site for an origin of life on Earth, the alkaline hydrothermal vent theory for the origin of life. And this is nothing more than serpentinizing systems where water spontaneously interacts with certain type of rocks, olivines and whatnot. And from that reaction, you have heat being released along with hydrogen and other compounds, and methane and CO2. And that can be those products of serpentinization can sustain microbial communities that rely only on hydrogen and CO2 as their source of energy and also as a source of carbon. That's very important, because that is one of the few metabolisms that we know on Earth that is completely independent from sunlight. Almost many other metabolisms, even some metabolisms that take place in anoxic environments, ultimately rely on the presence of oxygen, like, for example, sulfate reduction. Also, organisms that utilize sulfate, that use sulfate reduction, they still require oxygen to oxidize the sulfur into sulfate to have access to the sulfate, even if those organisms are light independent and they can live in the dark and in anoxic environments. So methanogenesis is one example where light is completely out of the equation. And obviously that's fundamental for any theories of habitability and life in ocean worlds. So now we have these interesting, was it me? Oh, I just touched the button. Okay. So now we have this interesting combination of things that we have a potentially habitable ocean, certainly an ocean that as far as we know, there will be plenty of microorganisms on Earth that will be happy campers in that ocean in terms of the pH and the salinity and the temperature and the access to resources like nutrients and energy sources. We also have an environment that appears to have at least one of the locations where we think life might have originated on Earth, the alkaline hydrothermal vents, where spontaneously fluids carrying hydrogen interact with fluids carrying CO2 through membranes, in this case, mineral membranes, the walls of hydrothermal vents, and through electronic exchange between those membranes, artificial geochemical membranes, you can trigger the synthesis of small organic compounds like acetate and formate, which can in turn become building blocks for more complex chemistry, leading to amino acids, the building blocks of life, and eventually the first cells. Anyway, this is all encapsulated in the alkaline hydrothermal theory for the origin of life, which is very interesting and predicts a number of interesting things about life on Earth and possibly on other planets like this. And at the same time, as I said, the coupling of hydrogen and CO2 justifies theories of metabolic processes independent from sunlight. So this is all very exciting. I mean, this is an astrobiologist's literally wet dream. Nothing 10 years ago, when I was mostly working on Mars stuff, you tell me that there's a place in the solar system where you have all these things happening. I'm telling you, you're nuts. But if that wasn't enough, it turns out that on top of things, the icing on the cake is that the plume is organic rich. And this is not often emphasized when people talk about Enceladus. They talk about the hydrothermal vents and the habitability and the plume and everything. But this is one of the most organic rich materials that we've come across and investigating other environments, certainly potentially habitable environments. So this is a picture of the INMS system. The CDA system, the Cosmic Dust Analyzer. That's the picture you see there. And together with the INMS, they detect a significant variety of volatile and non-volatile organic compounds. It appears to be the case now that most of what the INMS instrument detected in terms of volatile organic compounds, they probably are fragments of larger molecules that are non-volatile. And it's just that because I told you that the mission is flying so fast through the plume, it's literally breaking down every molecule in the plume into a plasma. And so originally they thought that they might be detecting things like HCN and things volatiles like this, but I think right now the current thinking is that what they found in the gas space in terms of organic material is probably mostly fragments of larger organic molecules. And the CDA found evidence of those larger organic molecules. In fact, it found evidence of two general classes of organic compounds, non-volatile. Some of them have low mass organic cations up to 60 AMU in molecular size. Where you have a reference, glycine, which is the smallest amino acid, has a molecular mass of 75 AMU. So those are organic compounds that fall close to what small amino acids might look like. And those compounds have spectral properties that are consistent with molecules such as amines. Although take that result with a grain of salt, because this is all based on laboratory extrapolations that might or might not really simulate what the instrument is detecting on Enceladus. But the fact is that they see evidence of these low mass organic cations. And then they see these really fascinating concentrated macromolecular organic cations up to the limit of detection of the limit of resolution of the instrument, which was 8,000 AMU. Really monstrous molecules, organic molecules sitting there. And they think that the breakdown of those molecules might actually be causing some of the products that they saw with the other instrument in the vapor phase. And those molecules, they appear to be mostly hydrocarbon fragments that probably or possibly contain oxygen and nitrogen in their chemistry. And this is an example of one example of a spectrum collected by Cassini that shows these macromolecular organic compounds. And one of the interesting features is this repeating mass that shows up every 13 or 14 AMU. And that's which they took this to imply that this is a fairly complicated network of aliphatic and aromatic compounds. This is the current best interpretation of that macromolecular material, what it might be. Cross-linked macromolecular or polymeric material with oxygen and nitrogen functional groups with aromatic rings chained, connected maybe with aliphatic chains. A lot of chemistry in there, but those two pictures are two representations of what that macromolecular organic material might look like. One is of a representation of insoluble organic matter found commonly in meteorites, and the other one is a representation of a humic substance. And this is actually our current best guess for what that macromolecular material might look like. We can't really tell based on Cassini data what it looks like because all that was turned into a plasma, so it's hard to reconstruct back what the original molecule was. And I think that's one of the reasons why we want to go back is to figure out what this material looks like without turning it into a plasma. But But obviously, this paints a very interesting picture of a potentially habitable environment with lots of organic material, some of it relatively complex organic material. And the other aspect of it is this question of why is the plume organic rich? If you run the numbers, Cassini was not the most sensitive instrument. They didn't have the most sensitive instruments. And if you run the numbers, the CDA, the limits of detection of the CDA, we're probably hovering around the millimolar concentration levels. They could detect things around the millimolar or low millimolar range. So if they detected organics in the low millimolar range, that's a lot of organics. That's probably translates to anywhere between 0.1 to a few percent organics in the ice grains. That's abundances that are only seen in things like, that are seen in places like chondritic meteorites. Now, the question is why do we have such high organic concentrations in the plume? I don't think that's telling us that the plume is an organic soup. I mean, the ocean is an organic soup. I think that's illogical, that the Enceladus ocean is so organic rich. And the Cassini team doesn't think that matters. This is what the current best interpretation of why the plume is organic rich is. The idea is that you have organics being produced in the ocean by whatever means, and those are slowly carried upwards into the water column, maybe by bubbles raising into the water column, and those bubbles carry organics with them. And those organics accumulate in the upper reaches of the ocean, right at the interface between the ocean, close to the water table. And this is a representation of what that might look like, where you have one of those fractures in the South Pole of Enceladus, which is maybe 5 or 10 kilometers deep. And about 1 kilometer, 2 kilometers below the surface, you have the water table. That water table is obviously in contact with vacuum. The vacuum, not vacuum because there is some water vapor pressure in the vents, but it's an interface that it's in contact with a low vacuum or a low pressure environment. So that entire system, certainly everything that is inside these tiger stripes, all these column of water, it's probably a very dynamic environment where you have a lot of boiling and dynamic currents and whatnot happening there. So the current theory is that this layer, and certainly the upper reaches of that layer towards the water table, they're rich in organic material that it's been accumulating over time. And when those bubbles burst, and they talk about this idea of a thin organic film coating the water table where these organic material accumulated, concentrated in. And the idea is that when bubbles burst, they eject this organic rich film into essentially vacuum, where it instantly freezes, and then it's carried out through by gas jets, it's ejected out into space. And that is a way to explain the sources of the 3 types of grains that Cassini saw. You have water vapor evaporating, and then some of it rapidly concentrates back into small icy grains. Now you get the type 1 grains that are purely water. If you have some ocean spray that goes into the tiger stripe vents and flash freezes, now you have some salty water freezing. That's how you get the type 3 salt grains, salt-bearing grains. And then if you have some of this organic rich film splashing because of a bubble burst and freezes instantaneously in the inside the tiger stripe vent, now you have the organic bearing ice grains. And then some of the water vapor can condense back on top of those organic rich material, and now you have an icy grain that has a lot of organics in it. Anyway, it's a neat model that explains the observations. And if it's not the right model, it's probably not far away because it's fairly simple. And in fact, we have similar processes happening, and I'm not going to talk about oceanography because I know there are oceanographers here, but my understanding is that there are processes happening in the oceans of the Earth that are very similar to this. Sprays can form easily by wave action or bubbles bursting. Sprays and aerosols tend to be enriched in organic material. Bubble bursting can be a source of enrichment for organics in ocean spray. And so these are processes that are possible and relevant and can explain the observations. And it's a very interesting place for oceanographers to start contributing to planetary sciences and astrobiology, because understanding how these processes operate and how fractionation might occur between the water and the material in the plume through these processes is very important to understand exactly how the plume composition translates to the chemistry of the ocean. Really nice place for oceanography to contribute to planetary. And I know people here in this group, in David's group, they've been working on understanding those processes. So I'm not want to get to a lot longer than I was expecting. Anyway, so what I really want to talk about is about what's next. I think next is we go to Enceladus and we try to determine whether there is life there. And the question is, how do we do that? And when I went into this, and when I came into this business of trying to figure out how to search for life on places like Enceladus, I went in with a lot of the ideas that we carry from other places, Mars and classic astrobiology, what kinds of biosignatures we might want to look for, which biosignatures make sense because they're not too Earth-centric, all that good stuff, all that discussions went in. Very quickly, though, I started thinking about how not to find ways of how not to search for life on Enceladus, because I saw a lot of what I thought would be bad ideas. If we were to implement these in a mission 20 years from now and spend $3 billion doing this, the chances that this is going to work, I think they're remote. So I think we really need to understand not what we want to do, but especially what we don't want to do. Eventually, I got frustrated and I said, this is the wrong question anyway. We shouldn't be asking how to search for life on Enceladus because this is not a scientific, that's not the scientific method. That's not how we do science. This is like looking for your keys under the lamp, under the street lamp. You're looking for things that you're just confirming what you want to see. This is not proper science. And I was happy to go back into the literature and dig out a couple of all these good papers from the 1960s, which one of the authors says this should be mandatory reading for any student in any university in the world. I think that statement still applies today. So I encourage every student today to read those two papers. One is from 1964 by J.R. Platt. And it's and in that paper, he argues for applying almost fundamentally a scientific approach that he called strong inference. Strong inference. And he argues that there is a reason why certain scientific disciplines advance very fast, while other disciplines they seem to stall and hit a wall and don't move and they do not advance very fast for long periods of time. And his argument in the paper is that those disciplines stop implementing this strong inference, which you will say, what's the big deal? Strong inference is defining an hypothesis, defining an experiment to execute that hypothesis, and then repeat the process to refine the possibilities that remain. And you say, that's the scientific method. We do that every day. Platt argued that we don't do that every day. In fact, we do it less and less. And I will argue in a second that when we say we're going to search for biosignatures and evidence of life on Enceladus, we're not following the scientific method. We're not defining hypotheses that are testable, and we're not refining those hypotheses based on the data we get. And the other experiment and the other paper by T.C. Chamberlain came out a year later. He makes even a more interesting and daring proposition. And he says, yes, we need to do what Platt suggests, but we need to do it in a way that he calls, we need to formulate multiple working hypotheses. You cannot just go in with a single hypothesis. And I won't go into the details. But his point is that if you don't have an hypothesis, it's like what I said earlier, you're subject of confirmation bias. You're just looking for things that you want to see with no hypothesis to test. If when you have an hypothesis, only one, that still becomes your child. And he actually talks in those terms that your hypothesis becomes your child. And of course, you love your child and you want your child to succeed. So you want your hypothesis to succeed. But when you have multiple hypotheses, now you have multiple childs. And you can't have a favorite, obviously. You don't have favorites when you have multiple childs. So if you want to really remove yourself from bias, you really have to have different working hypotheses of the same phenomena so that you can minimize the likelihood that you are ignoring possibilities and possible outcomes and possible explanations. And he captures that in this nice sentence that it's to consider every rational explanation of new phenomena and develop every testable hypothesis respecting their cause and history. So that armed with a family of hypotheses, the investigator can tackle the problem at hand without favoring any one in particular. And I would encourage anybody in the room that thinks about life detection and astrobiology to start thinking how much of this actually takes place in astrobiology. And I will argue not a lot. So I want to talk about the problem with biosignatures, because this is really what it's at stake here. We are planning to send missions in the next 30 years to places like Enceladus. We're going to spend billions of dollars. We're designing those missions around searching for biosignatures. And here is the problem with biosignatures. This is a quote allegedly from Carl Sagan a number of years ago, talking about a gentleman that in 1912, he said that life necessarily must be based on carbon and water and have its higher forms metabolizing free oxygen. And he said that this conclusion is suspect because the author is made of carbon and water and breathes oxygen. So there's even a vested interest in it. And that's a lot what happens with with picking biosignatures, and that is Earth-centric bias and tunnel vision. We're looking at ourselves in the mirror. So what we do when we search for biosignatures, when we look for biosignatures, we're actually playing an imitation game. We look at Earth life, and we say we ask what properties of Earth life we think life elsewhere might imitate, and then we look for those properties. It's not proper science because the number of possible outcomes from such a search of biosignatures is, one, is unconstrained, and two, too many outcomes are not desirable outcomes. The first and foremost outcome, and let's think of biosignatures. You can imagine your own personal favorite biosignature, a swimming cell, or a protein, or a DNA, or a polyelectrolyte, or an isotopic ratio, or a stromatolite. I don't care, pick one, anything that it's been thrown out there. One very possible outcome that searching for one of those biosignatures or many of those biosignatures is a true negative result. We don't find anything because there is nothing there alive, because either there was no origin of life, or because life eventually became extinct and there is no more life anymore and any signature has been gone. That would be a true negative. It's untestable, obviously. We cannot rule out the absence of life in an environment. We can rule out a negative. But this is a very possible outcome, that we search for biosignatures in those environments and we find nothing. Now, it could be a true negative, theoretically, but it could also be a false negative. It could be a false negative because that place is populated by weird life, that it's not making the biosignature, it's not using the same type of molecules they're looking for, or it's not fractionating isotopes in the similar way, or it doesn't swim, or it doesn't have a cellular structure. Or it could be a false negative because life is present, but we cannot detect it. It's just too low abundance, which is a very real possibility in environments like ocean worlds, where energy flux is very low. Or life could be present, but those biosignatures get damaged before we even detect them. And so they are undetectable. Now, how can we discriminate between a false negative and a true negative? You can't. It's impossible. Unless you do a lot of follow-ups and you bring samples back, and then you're spending tens of millions of dollars to do something that you didn't have to do to start with. And I think that's because you're focusing on biosignatures. There is even a possibility of false positives. You could have a positive detection that is not a true detection because either you're contaminating your sample, which is something we can mitigate against, but there are also things like mimics out there. There are things that can resemble biosignatures, and we need to constantly remind ourselves of the possibility of mimics. And only in the best scenario, we hit the jackpot and we get a true positive and we find evidence of that. Now, I'm not willing to bet $3 billion, $5 billion doing an experiment that can hardly discriminate between these scenarios, and only in the best possible case that we hit the jackpot, we find what we were looking for. This is not a good experiment. It's particularly not good because it's actually ignoring other possible alternative scenarios, like a prebiotic environment, which is also very interesting. It's also ignoring an abiotic environment, which is also very interesting. And I think we need to understand the value of prebiotic and abiotic environments and factor them in our strategy. And this is where the idea of multiple working hypotheses starts to percolate. We need these are our three favorite kits, not just one. Our favorite kit is not just the biological kit. The abiotic kit, such a thing, is also a favorite, and the prebiotic kit is also a favorite. All three of them are scientifically very compelling hypotheses, and we should pay each one of them equal respect. So what is the question then? After asking this question leads us, in my opinion, to that dead end of multiple negative results that are very hard to disentangle. I think the alternative question is not whether there is life in that environment, but what is the extent of organic chemical evolution in that environment? And this is a question that is grounded on well-known and principles. Principles we understand, theories we can apply, hypotheses we can build for those theories. And by testing these, by asking this question and testing those theories, we can make incremental progress, sometimes can be dramatic progress, depending on how we design our missions. And eventually, one of the possible outcomes, guess what, is detecting evidence of life on another world. But this is the guiding principle. And this is what motivates this framework that I'm advocating for missions that don't search for evidence of life. They try to understand the extent of organic chemical evolution in the environment. It starts with the theory of organic chemical evolution, which is widely accepted. Most people would agree that life, whenever it emerges from a prebiotic world, from a series of abiotic chemical reactions. It's not spontaneously created. The idea of panspermia doesn't remove the problem from the equation. It just moves the problem elsewhere. So I think everybody agrees that theory of organic chemical evolution is the leading theory. And in very simple terms, the theory of organic chemical evolution postulates a number of steps from abiotic to biological systems. It starts with simple inorganic precursors, hydrogen, CO2, things that can react, this chemical disequilibrium. The spontaneous reaction of those compounds generate small organic building blocks, things like acetate and formate and HCN and whatnot. There needs to be a chemical step from which these organic precursors combine into what we call biochemical building blocks, amino acids, nucleobases, sugars, carboxylic acids. These are the types of things we find in meteorites, and we make them easily in the lab. So this should be relatively common in any prebiotic or abiotic environments where there is this chemical disequilibrium and active organic synthesis happening. Now, at some point, this in the origin of life theory, somehow at some point, these building blocks need to start polymerizing and forming small polymers. And at some point, those polymers need to become functional. Some of them become catalytic polymers. Some of them become genetic polymers. And at some point, all this gets encased into some kind of membrane that looks like an organism. Evolution kicks in, natural selection. You get complexity happening, and then diversification. Now, this is obviously a very simple scheme, but these things need to happen for life to exist somewhere. So when somebody says, I want to search for swimming cells on Enceladus, you're assuming each one of these 7 steps took place already before you're searching for cells. And I call each one of these steps a miracle. So it's 7 miracles and change that need to happen before your favorite biosignature gets detected, if it's detectable. And so then you have the problem of alteration and whatnot that can completely mess up the whole thing. But this is a very interesting framework. This is a model of how we think chemical evolution operates. We have very little evidence that actually takes place. We'll accept it because it makes rational sense, but we have very little evidence that this is actually happening. We have evidence that stems number 1 and number 2 happen because we see stuff like this happening all the time in the lab, and we see the products of it in meteorites, but we've never gone from number 2 to number 3. That's the extent of our demonstration of the theory of organic chemical evolution. And I argue that planetary exploration, astrobiology should be about right now demonstrating number 3, that number 2 and number 3 can happen. Number 2 can happen in a habitable environment, and number 3 can happen in any environment. And the point I'm going to make is that by doing that, we're actually doing that life detection. We don't have to go all the way down before we start searching for life. We can already, this region of the continuum of organic chemical evolution is already a place where we can tease out abiotic from prebiotic from biological scenarios. And I'm really going slow, so I'm going to accelerate these. The other thing that I will mention that I think it's an important part of this framework is an idea that we put out a couple of years ago that we call the principle of chance and necessity in biochemistry. And this is a relatively simple idea. The idea is that when you look at our biochemistry, the biochemistry of life on Earth, you can actually tell that fundamentally it's the result of 2 processes. Our biochemistry reflects, on the one end, whatever was available prebiotically at the origin of life. Whatever building blocks were there, we incorporate those. That makes logical sense. And then there is an aspect of biology that it's a result of evolution. We invented it because we had to solve problems in our environment that require us coming up with new molecules that didn't exist before life existed. So we made the argument a number of years ago, and you might disagree, that biochemically is always going to have this dichotomy. Irrespectively of how it originates, it's going to have a component that reflects the prebiotic environment where that form of life, where it came from. And it has a component, and we call it necessity. And then there is the component that is random because it's the product of evolution and natural selection, and that is the chance. And this is just an example of how this is reflected, recreated in our own biochemistry. This plot shows the frequencies of the 20 protein amino acids in thousands of organisms on the Earth. And 10 of those amino acids, the ones you see in red, those are the ones commonly found in meteorites. And the other 10 are inventions from Earth life. They didn't exist before Earth life appeared. Or at least we haven't found them yet in non-biological environments. And so that reflects both the chance, inventions, and the necessity of our biochemistry, the prebiotic environment. Now, This is a bit of a convoluted diagram, but what this is trying to show is why is this important for us? When you look at abiotic environments like meteorites, comets, asteroids, and you look at their organic composition, there is not a lot of variability. If every carbonaceous chondrite had a different family of amino acids, I think we have a big problem. But that doesn't happen to be, that's not the case. We tend to always find the same types of amino acids overrepresented in those types of environments, in comets and in meteorites. For example, glycine, alanine, those are very common in all these environments. We don't find a lot of other more complex amino acids. Certainly, we don't find amino acids that we use in proteins that don't exist like otherwise, like the complex, thick, bulky amino acids. So what this is telling us is that if you take two environments that are completely different, like the Earth, early Earth and Enceladus, and let's assume that both are prebiotic, even if they are very separate, there's probably a chemical overlap because they're prebiotic and they're basically generating the same types of molecules. There is an overlap in the prebiotic environment. Now, the moment life appears in that environment, that overlap starts to disintegrate because every biochemistry is going to start diverging from each other, because the biochemistry on Enceladus is going to evolve its own problem, its solutions to its own problems, and the terrestrial biochemistry is going to evolve other solutions to other problems. So at that point, the chemical space that is possible for biochemistry starts to open up, and this is what it's represented here. The chemical space for evolution is almost unlimited. We can come up with all kinds of inventions to solve problems like DNA and RNA and hemoglobin and things like this. But at the prebiotic environment, there is a lot of overlap. That is to say that if we look at the qualities of our biochemistry that reflect the prebiotic environment, those are more likely to be represented in other biochemistry than the aspects of our biochemistry that are obviously the result of evolution. I don't think I'm stretching the logic here. I think it makes logical sense. And so what does that mean in terms of the framework for organic chemical evolution that I was arguing? My prediction and hypothesis is that those aspects, that early part of chemical evolution, the first few steps of organic synthesis, number 2, and polymerization, number 3, those are, I think they're going to be necessary for any form of life to evolve, at least in water-based environments. Everything that comes afterwards is chance. That's evolutionary products, and who knows what that might be, what that might look like. That depends on the actual planet and the conditions in the planet. So by focusing on these two preliminary steps, we're targeting a chemical space that is likely to be common, whether life exists there or not. And if life exists there, it doesn't matter how complicated it is. I think we're going to have a common overlap in that chemical space of steps number 2 and number 3, building blocks and the first polymers. And I've been using the case of amino acid. There are other types of molecules that that you can apply the same logic to, and essentially are the 4 building blocks that you see there: amino acids, nucleobases, sugars, and carboxylic acids. Each one of those molecules is a candidate to be present prebiotically, abiotically, and I would argue biological. The question is, how can you discriminate between all 3 scenarios? And I'll show you a couple of examples of how we might do that. This is a plot that shows the distribution of some amino acids in a lot of meteorites. And so the amino acids you see there are at the bottom: glycine, alanine, serine, AIB, aspartic acid, glutamic acid, and valine. All except AIB are we use for proteins. And what you can see is that the small amino acids, and those are towards the left, glycine and alanine, are overrepresented in AIB. By the time you move into aspartic acid and glutamic acid, their abundances, the relative abundances, are very small. And especially that's the case when you combine the little amino acids, like these 3 that are small ones, with 4 of the large ones. The dichotomy is even more striking. This is the same plot, but now we're not measuring meteorites, not analyzing meteorites, we're analyzing samples from Earth, terrestrial samples with biology in it. Now the distribution is very similar, is very different, because biology doesn't care about which molecules are easier to form. Biology cares about which molecules are important for me to survive. So if I have to make a lot of very complex stuff, I'm going to spend the energy building that complex stuff. And that is reflected in the distribution of amino acids in that sample. So I didn't really talk about a biosignature. I talked about amino acids, searching for amino acids because of prebiotic reasons, abiotic reasons, and overlaps and all kinds of crazy things. But it so happens that in doing so, you can actually start to discriminate biotic distributions from abiotic moons. That's the beginning of a testable hypothesis. And this is what the combination of both data sets shows. In an abiotic scenario, this is the types of distributions you would predict. And in a biological scenario, these are the types of distributions you would predict. And if you really hate to predict what a biological distribution might look like, that's okay. Ignore the bottom one. The point is that if we see something that doesn't look like the top one, something really fun is happening in that environment that we cannot explain abiotically, at least not with our abiotic chemistry. Now we have two working hypotheses for the case of Enceladus. I could hypothesize that organic material in the Enceladus ocean is the result of the activity of organisms in metabolic processes in the water column. And as a result, organic matter in the grains will show a degree of functionality and selectivity and complexity that points to evolutionary processes. For example, I'm going to see distributions of amino acids where larger compounds are overrepresented or are in abundances that are not explainable abiotically. And then there is the abiotic hypothesis, which is also a great hypothesis. I love it. And that tells the opposite, that the organic content in the ocean is actually abiotic. And as a result, the organic composition that I'm going to see, it's entirely explainable by invoking kinetic and thermodynamic principles, which predict that only the small molecules are going to be represented in those environments. Now, I can do that with measuring multiple qualities. These are three things we can measure on amino acids: chirality, relative abundances, and isotopic ratios. Each one of them has an abiotic and a biological expression. And so each one of them can support one hypothesis or the other. Now, you might call one of them a biosignature and the other not. That's fine. But I don't even need to call them a biosignature because it's just testing. This is just measuring properties and then making interpretations based on those results. In this case, 3 results. But then if you add another type of compound like lipids to the equation, now you're adding 2 or 3 more parameters. Now you're playing with 6 different properties, each one of them telling you a story about the origins of those materials. And I think with that type of information, now you can start making informed predictions of what the origin of those compounds might be or might not be. This, I argue, is the type of science we need to do with astrobiology missions in places like Enceladus, rather than focusing on expecting to find things that are smoking guns, that if we find them are obvious evidence of life, the chances of finding them might not be too high. And I'll close with a few slides about orbital under. I want to really leave time for a few questions, so I'll go over it. This is just to show that this is not a pie in the sky. I think we are ready to start working on missions that can execute this type of science. This is an example of a mission concept we put together a couple of years ago, which would do a whole lot of different measurements, including high-resolution mass spectroscopy, inorganic chemistry, separation mass spectroscopy like GCMS chemistry, capillary electrophoresis to look at amino acids. And then it will look for a couple of biosignatures using nanopores and microscopes. And I think this is a healthy combination of the types of science I was advocating for, and then some of this, swing for the fences type of instruments that if you find something, it's going to be amazing. But if you don't find it, we still have all the other science to deal with. And then the mission would have a lot of interesting context information about the structure of the moon and the structure of the plumes and how those plumes originate. It's I think a very complete package. The mission itself would spend about 1.5 years orbiting Enceladus, collecting samples from those plumes and analyzing the chemistry of those samples, and at the same time making radar measurements of the moon and on the surface, looking for a safe place to land. And then the same spacecraft would itself land on the surface. Once you're orbiting Enceladus, landing on the surface is not a big deal. The delta V is very small. And so then it would spend 2 years measuring on the surface. And then on the surface, it would be collecting plume fallout. So a lot of the plume material falls back out on the surface, especially the big grains, the ones with a lot of stuff in it. They fall back down. So you could be collecting that material. And then a scoop or any other sampling material could be collecting plume deposits that have been accumulating there for thousands of years. So at that point, you have pretty much unlimited amounts of sample to play with. So you can really push the sensitivities of your instruments. I think at the end of a mission like this, you're fairly certain of what you didn't find and what you found, and you can make some informed decisions. And I was happy to see that the Decadal survey recommended these as the second highest priority new flagship mission for the next decade, which means it's not going to fly in the next 20 years. That's NASA's way of telling you thanks, but no thanks. But what this is telling us is for the first time, there is an astrobiology live detection mission at the forefront of one of the most important programmatic documents that NASA looks at. And the prediction is that in 10 years from now, this is going to be not the second choice, but the first choice. And so this is very exciting for those of you younger in the room, because by the time this thing happens, if it happens, we're probably going to be in the mid-2050s. So start exercising, go to the gym, eat your veggies, and quit smoking, because it's going to be a long way. But I think this is very exciting, and hopefully I've made the case to you today that this is worth investing on, and this is the right science to do with this type of mission. So I'll be happy to take questions. Thank you for.
All right, open to questions. Zach.
Concentrate.
It's a big concern, yes, and it's a place where we could use the help from people who have experience understanding how this process is happening in the Earth's oceans. Now, how much bias? David can certainly talk about this, because they've been looking at it in the gas phase, and in the gas phase, you would expect a lot more fractionation to take place. How much fractionation you can have between different types of amino acids? That is not a question that I'd say keeps me up at night, but it worries me. But that is the type of science that you can promote with this type of approaches. It shouldn't be a concern. It should be a motivation to actually test for it and understand it. There is certainly, I know that oceanographers have seen some sort of fractionation between amino acids in the process of aerosol formation. They've also seen a big enrichment factor of organic matter. So we will have to pay close attention to that. I'll be happy if in 50 years, somebody from NASA goes in front of the TV and said, there is life on Enceladus because there is almost no glycine and there's a lot of alanine. And then everybody else, closed a gasket and said, I'm going to prove you wrong. That's the way science works. That's the way it should work. But at least we're going to start from actual data, an observation, and then we can fight it off whether the observation is reflecting the actual environment or it's an artifact. But I hope that's a great problem for astrobiologists to have.
Yep.
Yeah. Glad you asked, because that goes into the whole agnostic biosignatures thing that it's big now. And if I think about that, the idea of assembly theory, and to me, they're saying the same thing I'm saying with different words. Essentially, what they're saying is, what is the degree of chemical evolution in this system? They're just saying we can quantify it, but then they say, and then we will assume a threshold, and that's where it stops being agnostic, right? That's where the agnostic question starts to be interesting. So what's your threshold? 10, 15 steps? I mean, that's a decision you made based on biochemistry, But everything else they say, I wholeheartedly sympathize with, because essentially what they're saying is let's assess. That's a test for organic chemical evolution. To me, it's a similar test for racemization. The amount of racemization is an indicator of chemical evolution. The relative ratios of abundance is an indication of chemical evolution. Polymerization also, although obviously that's tricky. Isotopic fraction, molecular isotopic fractionation is an indicator of chemical evolution. So I think it fits perfectly in it.
When you discuss
Well, I don't know if you can extrapolate from just an amino acid distribution. Maybe it's a good question. I would ask them that question. Take even this distribution of amino acids a function of size. Okay, is that telling us? Although in this case, that it's not a threshold, or we still use glycine. If we didn't use glycine, we wouldn't be here today. So we still use some of the little stuff. It's just that relative abundances are different. So it's not so much in the complexity of the things we use, it's part there, but it's, and if you look at those distributions that I mentioned, I'm not looking, I specifically said amino acids that are prebiotically abundant. So aspartic acid is the most complex thing that I had up there. And that's an abiotic amino acid for all intents and purposes. So it's not a question of how complex it is, it's how much of it the system is capable of making. And if it's making a lot of it, there's not many abiotic processes that explain that source that we know of. In fact, before we go, then what I would say, even doubling down on what I just said, that should be our null hypothesis. If we really wanted to be conservative and do proper science, our null hypothesis should be there is no life in this environment, and therefore all the amino acids are going to be glycine. Carboxylic acids are going to be less than 10 carbons long, and then you pick the other best predictor, and then prove me wrong. And anything that is not that, it's going to be an interesting question. I'm not going to say it's life, but it's going to be a very interesting scenario.
In your slides, you also, on your diagrams, had a spiky distribution. That's, you know, what Chris McKay calls the Lego principle. Like you make things out of units of isoprenes or whatever, which is what biology does. It doesn't have a smooth distribution. That's what abiotic does. Right? Yeah. Don?
So the ocean floor is probably fairly.
So
it's just isolated. There's a lot of people that are interested in place.
oh yeah, and there are other models. The clay is not the only model, and that's a bit outside of my expertise, but they also talk about carbonate deposits, and talc quartz deposits down there.
Probably a lot more clay than you make.
Yeah. Now there are a lot of open questions, so that could be a plausible scenario. There's a lot of stuff going on down there. There is nothing else going on elsewhere. Everybody's down at there is the part, that's where the party is happening, and the rest of the moon, there's nothing going on there. But that's not what we see in the plume. We see a lot of organics in the plume. Those organics are coming from somewhere. So either things are getting mixed, or there is a process of carrying organics very effectively. If the plume was organic poor, I would say there is a good chance that we're looking for things and we don't find them because the ocean is not mixed, is structured, or because everything is concentrated at the bottom. But for once, I think first time in my career that the universe cooperates. And so there is a sample with a lot of organics on it. So I don't worry so much that the ocean is mixed or not mixed. I think those are discussions that are taking place, but I think for the case of life detection are irrelevant because the organics are there. I don't care how they got there. The fact is that they're good. So we have a signal we can try to tease out. Now, if we go there and we don't find any of the organics we're looking for, maybe you can start wondering, well, is there a process by which you could distill the organics in a way that only the hydrophobic hydrocarbons flow to the surface and everything else stays? I don't know. You can come up with things like this, but just having that organic signal out there, everything else, all the other scenarios are hypotheticals, and to me they're not that interesting. But yes, to your question, yes, it's interesting that a lot of things can happen there. There is a lot of processes that we're not considering, water rock reactions, that I think very interesting, that can lead to productions of oxidants, for example. Sulfide minerals interacting with water, we could potentially generate other sources of electron donors and electron acceptors, like sulfates, that we're not considering in our metabolic models. And those could be happening on the ocean floor, and could be a very interesting addition. And obviously clays have impacts relevant for the origin of life and all kinds of things.
But any other questions? Yeah.
Yeah, I guess this search of smoking gun.
Okay,
So
great.
it seems like so yes, that's
here first, so it's other here.
Right,
So,
right.
so I'm not sure all the Zoomers, if they're still on there, can hear the questions that far back, but I think Yuck was saying we should look for a smoking gun for life.
Yeah, try to make a case, yeah.
Instead of all these bits and pieces that he doesn't like very much. What is your smoking gun?
I guess just in general, like just try to compare to,
Remote chirality or something?
yeah, or like a swimming like fish.
A fish.
That's the kind of, whoa, I think you just made me lose my voice.
Fish did it.
The fish did it. A lot of people, that's what they say, what would convince me that there is life? And then they say a swimming cell or something very complicated. But I think that's a bias. I'm not saying you're biased, and I respect your opinion. But I think that we underestimate, and this is really a personal opinion, we underestimate how easy life detection is. I think life detection is really easy. We can do it anywhere, all the time. What's really hard is life characterization, which is what we do most of the time as microbiologists on Earth. We spend most of the day trying to figure out what life is doing, not whether there is life there. And we get those confused very often. I've done field work in some of the places on Earth where there is almost no biomass. Zero problems finding life in those environments. We do it all the time, doing these types of measurements or doing other types of measurements. But now you ask me, what are those microbes doing? And I have no clue, because it's exceedingly complicated because of signal to noise ratios, because of how difficult it is to extract the right molecules. That is the hard part. So my prediction is that whenever we really go after detecting life, and I think this is the way to go, we will find it if it's there. I don't think it's going to be a problem. The problems will begin afterwards when we start wondering, so what do they do? What do they look like? What do they taste like? That's when we're going to have a lot of problems to do, because that's the difficult part of doing microbiology. I would encourage any microbiology in the room to say the opposite, but I honestly have zero problems finding life in the, people have found life in ice cores in the Antarctic ice shelf. I mean, easy, no problem. You just melt enough water and you'll find it. And but trying to figure out, are they dead or alive? That's taken several PhDs just to figure out that question. But that's not life detection, that's life characterization. And I think what you're advocating for, it's fundamental, it's life, but I think it's life characterization, and it's the next step. After we've found something interesting, let's dig deep into that and see what's there.
So Alfonso's voice is declining. So let's thank him once again.